In this video, we're going to discuss the big O of binary search tree. So this is the slide from the beginning when we introduce binary search trees. We say the reason we want binary search tree is that we want to have something that can do insertion, removal, and search all in O of log n. So did we accomplish this? Is binary search tree able to do that? Well, the answer is slightly complicated. So let's look at a balanced binary search tree first. In fact, this is a perfectly balanced binary search tree because every single node has two children except the leaf node, which has no children, no child. So the tree's height, which is the height of the root node, is 3 in this case, and you hopefully can see this, that it's approximately the function of the number of nodes in the tree, and that function is log of base 2 to the n, where n is the number of nodes, and n minus 1, we usually don't care about the minus or plus 1 when we talk about big O, as you remember. So to verify that, yeah, this tree has 15 nodes. You can kind of think of that as 16. So log of base 2, 16, that's 4. 4 minus 1 is 3, which is the height of the tree. Okay, so what happens when we want to find anything in this tree? How many comparisons does it take? Well, it takes at most 4 comparisons to find anything, right? So one potential path is, we start at the root, we go down one level, another level, and finally, on the 4th comparison, we guarantee to reach a leaf node in this tree. So 4 comparisons, the height is 3, so it's the number of comparisons is really the height plus 1. So it's almost exactly the same as the height, especially when the tree gets large. And remember, the height is a function of the number of nodes, which is n of log of n. And so so search is really O of log of n for a balanced binary search tree. And when we think back to how insertion and removal works, that's also true, right? Both of those operations are log of O of log of n. Okay, what about this tree? Well, first of all, is it a binary tree or a binary search tree? Well, yes, it is, because each node has no more than 2 children, so that is true. Each node only has 1 child, except the leaf node, of course. Now, this binary tree, though, is unbalanced. It's an extreme example of an unbalanced tree. Now, it has the same height as the previous balanced binary tree. The height is still 3. But as the number of nodes, what is the height now? The height is the number of nodes minus 1, because the number of nodes is just 4, right? But height is 3. So, and especially if the tree is large, then the height is really the same as the number of nodes, which is just n. And remember, the search operation takes approximately on the order of the same number of the number of comparisons for the search operation is approximately the same as the height. So the search operation is therefore O of n, which is linear now, and also is the same for insertion and removal. So what we can see then is the big O of the search and insertion or removal operation of a BST really kind of depends on how balanced the tree is. And from what we just saw, on average, if things are kind of large and random, it should be O of log of n. But in the worst case, in this case, it is O of n. And yeah, and if this can be proved rigorously using math, but that would not be our focus in this class. So the moral of the lesson is, for binary search tree, is very, very important to keep it somewhat balanced, as balanced as we can. And that's actually, we'll talk about that next week. So I'll leave you with one last exercise, and that is, we know the extreme unbalanced binary search tree is terrible in terms of performance. And so let's think about what kind of data would actually produce that kind of unbalanced binary search tree. As it turns out, it's the sorted data. So we can actually show this very easily. I already written the code to do that. And so basically we're going to insert the numbers 0 through 9 in order into the binary search tree. And let me run this now. And there we are. We can see that the tree, again, tilt your head kind of sideways, it starts at 0. Because every number is increasingly bigger, so it always gets inserted to the right subtree.